So the intention of this video is to help you with assignment 6, the first half, the MOPS on forces in two dimensions. And I'll try and do another video on circular motion. So feel free to jump around this if you're looking for particular problems that you're trying to solve. I'll try and do a random represented group of problems from the forces 2D part of the MOPS. So before we begin, some general comments. So my goal for you in learning physics is that you develop an ability to think about the physical world in general guidelines and general laws and general principles that apply to a wide variety of problems. So you're not just looking for, oh, which equation do I need to solve this problem? No, you're asking questions like, oh, is this a Newton's second law of force problem? Is it a force problem where the sum of the forces is 0 and it's balanced? Or is it a problem where the sum of the forces are not 0 and it's an acceleration? So you're thinking in general terms. And when we're doing the problems in this section, there is a format. And if you look at the equation sheet, you'll see something like this. So you'll notice when I solve these problems, I'm going to follow these 6 steps. I'm going to do a diagram. And even if it's given, it's sometimes good to just do the diagram yourself. If you're a kinesthetic learner like I am, it just helps to write things out. Then you're always going to draw a free body diagram. If you're not doing these with a piece of paper and a pencil and drawing free body diagrams, your learning is going to be greatly diminished. And then once the free body diagram is, this is the equation we're using, but it's a vector equation. The vector sum of all forces will be equal to the mass times the acceleration. This is Newton's second law. It's a relationship. It's not an equation, it's a relationship. It's a relationship between force, mass, and acceleration. It's a relationship between the net force and the motion that you get from the net force. But since it's a vector equation, we always divide it into these two parts. You'll see me do this. And in the beginning, you can just do it because you're told to. But hopefully over time, you'll understand why we're doing this. We're doing this because this relationship holds true from the smallest atom to the largest galaxy. It's a very, very powerful physical relationship that's true throughout the physical universe. And in order to be able to sum up the forces, that's why we draw the free body diagram. So I'll emphasize this as we do the problems. Then once this is done, do the symbolic algebra. Don't jump in and substitute numbers. Just do the symbolic algebra and then wait till the end to do the calculation. And once you've done the calculation, then you look at your answer and you think about it. Does it make sense? Is this a reasonable number? Because often if you have a wrong plus or minus sign, you'll get a number that's clearly wrong. So thinking about the physics can help you avoid getting a wrong answer because of a minor mathematical error. Okay, so I'm going to keep this in mind and we'll start doing some of the problems from assignment 6. So section 1 is a review of vectors. And I'm going to keep bugging you. Remember, when you do these problems, you have a set of equations that will solve vector problems. There's 4 of them. This is all you need. But try to be understanding, develop your intuition about vectors. Vectors have a magnitude and direction. We represent them with arrows. But when we add them or combine them, we have to do it by components. So we always find the components of the vector. And the equations for finding the components should be obvious. If A is the vector, and we want to find its components. The AX is the cosine because it's the adjacent side, and the AY is the sine because it's opposite the angle. This is when we use these angles from the positive x-axis. Otherwise, you got to be careful. If you have a different angle and it's not from the x-axis, you can't just blindly use these equations. On the other hand, if you have the components and you want to find the vector and the direction, you have these two equations. And these should be immediately obvious. Vector components are always perpendicular to each other. They form a right triangle with the vector. So the two components squared will give you, and notice the notation, vector A, the magnitude. This means the magnitude of vector A. It's always a positive number. If AX or AY is negative, it will square to a positive. So you got to be careful when you use this that you put your parentheses in the right way. These two numbers will always be positive. And so if you get a magnitude which is smaller than a component, you know you've made a calculation error. And it should be obvious that the angle is going to be the inverse tangent because tangent is opposite over adjacent. So these equations, you have them on your equation sheet. You should know them, but you should understand where they come from. So with this, you do section 1. Nobody yet has asked me any questions about that. I assume for most people it's going okay. So this practice and this ability to work with vectors well is important from now until the end of Physics 2. It is so important in physics and many courses in engineering, so learn it well. So we're now in section 2, and this is one of the problems toward the end of section 2, or one of the harder problems. And if you walk through the others, it will prepare you to do this. And if you understand how to do this, it'll also help you answer the earlier questions. So once you understand, here's how I look at this diagram when I see it. The first thing I look at is the forces in the y direction should be balanced. And so what I would do, the first thing I would do actually, is with this diagram, I would draw in the components because I can see we have to do this x and y, right? So let's draw in the components, and I usually draw them in as dotted lines because they're not separate forces, they're components of the applied force. And so this would be, I'm not going to write the app applied, I'm just going to write this is Fy, the y component of the F app. And this is the x component, and we will need those. And the way we get those is through the cosine of the angle. So even before I begin this problem, I'm going to calculate what those are. I haven't given you the numbers yet, but we'll do that in a minute. And then I look at this thing and make sure that it looks, so the normal force and this force are the up forces. And so these plus this should equal that, right? Why? Because there's no acceleration this way. There's no motion this way at all. And then I look at the diagram and I see the friction force is smaller than the x component of the applied force. So I know there's an unbalanced force in the x direction, and this is going to accelerate, and they ask me for the acceleration. So even before I begin the problem, even before I look at the numbers, I just try and wrap my mind around this physical situation to make sure I'm understanding it. Okay, now I'm going to give you the numbers. Okay, here are the numbers. 8.2 kilograms for the mass, 43, if you can't read it, 43.8 newtons for the applied force, and the coefficient of friction, mu k, 0.29. So the force of friction, I need to make a video on that. Remember that the force of friction is the coefficient of friction, and I write mu k because there's sliding friction and static friction, times the normal force. So I'm going to make a separate video. I realize this should be a video talking about friction because that can be confusing to people. So look for that video. But anyway, this is the equation you want to use for friction. So now calculate what they ask for is the normal force, the friction force, the gravity force, and wait a second, and the acceleration. So 4 things. Acceleration equals. So remember, I'll just prompt you and then try to do this. The first thing you want to do is to get these 2 components from this and the angle. Oh, I forgot to give you the angle. You need that. 34 degrees. So the theta is 34 degrees. Okay? And so first thing, I'll just get the components. And then the next thing that you're going to do is do sum of the forces, x and y, like this. And sum of the forces, y. See if you can do this. If not, I'll show you how to do it. And the sum of the forces, y equals 0. And in this problem, the sum of the forces, x, do not equal 0. And so by that method, you can get all these numbers. So go ahead and give it a try. Don't just watch. You'll benefit a lot more if you do it. And at the point you get stuck and you're not sure what to do, you can come back to the video. But do it as much as you possibly can before you watch what I do. Okay, let me show you what I did so far and see how you're doing. So the first thing I did was I did Fy equals F cosine theta. So 43.8, sine theta, excuse me. 43.8 times the sine of 34 degrees gave me this number. I hope I didn't make a mistake. And Fx is 43.8 times the cosine of 34 gives me this number. And then I also got F grav because I'm going to need that. And F grav is mg. And so I took the m, the 8.2, and multiplied it by 9.8, and I got 80.36. Okay, now I'm going to get the normal force, I got to use some of the forces in the y direction. And notice, this is what you should be writing down. Practice the same format that I'm using. You'll be so much more effective at solving problems if you practice this formatting. So some of the forces in the y direction equal may, I didn't write it, equals 0. Why? Because ay is 0. So now this says sum up the forces. So I go to my free body diagram. I see Fn is a y force. I see Fy of the applied force, and these are both positive. And then I see the gravity force is negative, so I put in the negative sign, and I set them equal to 0. So I summed up the forces, and I set them equal to 0. Now I want to solve for Fn, so I do the algebra, and I get that Fn equals Fg minus Fy. Okay, so I've done the algebra. Remember, algebra, then the calculation. So 80.36 minus 24.49. I know my writing's not very good. And I get a normal force of 55.87. So I can write that up there, 55.87. And then I have the normal force. And now I'm going to think and check. So what I know is that the normal force and the Fy force should be equal to gravity. Did I get that? Yes, the 24.49, which is up, and the 55.87, which was up, and if I add those together, I'm going to get the 80.36, which is the gravity force down. So this looks good. I'm going to take that number. So now we're going to go to some of the forces in the x direction, but we have the friction force, So use the coefficient and the normal force to get the friction force, and then do this and get the acceleration. Go ahead, try that. Okay, you can check your answers. So I calculated the friction force to be 1620, whoops, I forget the units, newtons. And so then I came over here, and I'm going to do this. Sum up the forces in the x direction, set them equal to the mass times the acceleration in the x direction. The net force in the x direction will equal the mass times its acceleration. So in the positive direction, we have Fx, the x component of the applied force. And in the negative direction, we have the friction force. So we subtract that. And that will be equal to the mass times the acceleration. So I do the algebra, step 4, and I get that Ax equals Fx minus Fric over m. This is the net force divided by the mass. For the net force, subtracting 1620 from 36.31, I get 2120.11 divided by the 8.2 kilograms, and I get 2.45 meters per second squared, and we're done. So let's go to a new problem now. So I'm going to skip over section 3, which are equilibrium problems, and go to 4, where there's a series of problems that involve hanging signs or hanging objects. So this point could be any object, a sign or anything. And there are two strings at equal angle, or two cables at equal angles, holding the sign up, and what's acting down is the weight of the sign. So these two things have to support the sign. And so what you want to do is you want to look at this situation, keeping in mind the following. And that is Newton's second law. So we have our usual, this is a free body diagram. We have our sum of the forces vector equation, which we always separate into components. And so because this is in equilibrium, the sum of the forces in the x direction, which is always equal to max, in this case will be equal to 0. And the same with ay, it'll be 0 because it's stationary. So this is an equilibrium condition. And so with that in mind, we look at this and we know that the tension force, I'm just writing it Ft instead of Ftens, and Fg instead of Fgrav, that's mg. That what we know is that in the x direction, the only two forces are the x components of the cables. So they have to be equal and opposite. And that's because the tension forces are equal and the angles are the same. And then there's going to be two y components. So the strings are both holding the sign up with the y components and pulling equal and opposite on each other with the x components. So if we look at the sum of the forces x, we get that this has to be equal and opposite to that. But when we look at the sum of the forces y, we can see that this plus this has to equal the down force. And since these are equal, we can write over here 2 Fty, or Fy in the mop, minus mg equals 0, or 2Fty equals the force of gravity, or mg. So each y component has to be 1/2 the weight. But if we want to get the tension force, that's going to be bigger than the y component, and we use our trig relationships to do that. So this idea is what you need to know to do this section. Let's take one of the calculation problems at the end and do it together. So here's the problem I chose. Angle of there were two cables, two tension forces. The angle's 48.1 degrees to horizontal, so it's symmetric. And the weight of the sign is 58 newtons. So the newtons is important. If this were 58 kilograms, that would be a mass, and I have to multiply by 9.8. But when you have 58 newtons, that's it. That's the Fg. That's the weight. That is the mg. Okay, so to solve this problem, what we'll notice, like we just talked about, the x components are going to be equal and opposite, so they balance. But you're going to have two y components, which are equal, and each one of them, since they're equal, will be half of the weight. So we could actually do this in our head. The y component is going to be, for each one, is going to be, what, 29 newtons. But the way you want to do this out is to write down sum of the forces in the y direction equal MAY equals 0, and then solve it that way. So try and do it on your own before you watch me do it. It'll be much more effective if you do it yourself. Okay, I hope you got it. So the sum of the forces in the y direction equal MAY, and so we have FT plus FT minus FG equals 0. And so we get FT, don't look at this, FT equals FG over 2, because this will be 2FT, they're equal. But FTY, excuse me, FTY is equal to FT sine theta. The FTY is FT sine theta. And so when we do all that, not very well written here, we get FT equals FG divided by 2 divided by the sine theta, and the number I get is 38.96 for the tension in either cable, because they're at the same angle and the tension is the same. Okay, not too bad. Let's go to the next section. So the next two sections involve objects on inclined planes. And what you should know about this is there's two different situations. One is when we put an object and there's no friction and it slides down the plane. And the other, when we put it on an inclined plane and there is friction, and then it's going to slide down slower, or if the angle isn't steep enough, it might sit there stationary. So we're looking at two situations, with and without friction. And in order to do these problems and make them easy, it makes sense to put the x-axis along the track. So we're going to tip our x and y coordinates to match the problem. And at first that may seem like, oh, can you do that? Yeah, you can do that. And it just makes things easier, especially if there's an acceleration. Then the acceleration will be in one direction. There'll be no components to the acceleration. So remember, our way of analyzing these problems is diagram, here it is, and then I'm going to do a separate free body diagram, although in some cases the mop mixes them. So without friction, there are only two forces. There's the force of gravity, which is straight down. And there's a series of questions that will make sure that you know that the force of gravity always acts straight down toward the center of the Earth, and that the normal force, normal meaning perpendicular, the F norm, is always perpendicular to the track. So if that force is in any other direction, either of those, they're wrong. And if there's a friction force, that's parallel to the track. So we could draw it at the bottom of the block or the middle of the block, and it would be this way. That would be your F fric. And so, depending on whether there's friction or not, there's two or three forces. And because we're putting the x and y axis this way, the Fn is a y force, the F fric is an x force, but the gravity force has two components and you need to show them. One is along the y-axis, and the other is here along the x-axis. And so if this is mg, fg, which is mg, and the angle of the track will be this angle in the free body diagram. That's just the way it works out by trig. And so because our x-axis is this way, the friction force is x, the normal force is along y, but this has components, a y component and an x component. And since the vector is fg or mg, and since this is the angle, it turns out, because of the trig, that this y component is fg or mg cosine theta. Why? Because it's the vector, the y part is adjacent to the angle, and opposite the angle, this one here is going to be mg sine theta. And these components have physical meaning. The meaning is that the y component of the gravity force is what holds the block on the table, on the incline, and the x component of the thing is gravity force is what makes it slide down. And so it makes sense to divide these into these two components. Gravity is doing two things. It's making the block slide, and it's holding it onto the incline. So when we do the analysis, sum of the forces x and y, we're going to use this as the x and y axis. And when you get to do those questions in section 5 where these are at wrong angles, if the normal force points straight up, it's wrong. It's supposed to be perpendicular. And if the gravity force points in this direction, it's wrong. It's supposed to be straight down. And the friction force is always parallel to the surface, as the normal force is perpendicular to the surface. So do those carefully, and you'll save yourself from making mistakes on the quiz. Okay. Let's do one problem together from section 6. I picked a friction problem. And the way the MOP does it is they have the normal force, as I said, perpendicular to the track, the friction force parallel to the track, gravity straight down, but they call this x component F perpendicular because it's perpendicular to the track. That's what I called FGY component, and then the FGX component they put up here, and they call it F parallel. And if you look at it, these things are registered in a lighter color, and I draw them as dotted vectors because there is only 3 forces. There are not 5 forces. Don't get confused. And so F parallel, remember, is FG sine of this angle, which is the track angle, and this is FG or MG times the cosine, because it's adjacent, of the track angle. And so what you're asked to find is these two components, this force, the net force, and the acceleration. Let me write that down. Okay, so here are the quantities that were given. I took this, whoops. The mass is 3.34 kilograms. The angle of the track is 16.4 degrees. So the coefficient of friction is 0.112. And here are the 6 things we want to find. The normal force, I just wrote Fn. F parallel, can't even read it. F perpendicular, that's the perpendicular symbol. F fric, F net, which is the same as sum of the forces in the x direction, and A, which is AX. So as always, you're going to do it this way. To get the y forces, you use this, and to get the x forces and the acceleration, you're going to use this. So go ahead and try to do the whole thing yourself, and then you can come back and check your answers against mine. So here's what I did, assuming I didn't make any calculation error. I hope not. So the first thing I did was to find F parallel and F perpendicular, because in order to find F norm, which is the first one, I need this. And so I know FG is just mg, so I take the 3.34, multiply by 9.8, and then to get this one, I multiply by the sine of 16.4 degrees. So 3.34, 9.8, sine 16.4, and I get the 9.24 newtons for F parallel. Then F perpendicular is the 3.34 times 9.8 times the cosine of the 16.4, and that gives me 31.40. And because the sum of the forces in the y direction are 0, these two have to be equal and opposite, and so the normal force is 31.40. And since the friction force is the coefficient times the normal force, I just take the 31.40 and multiply by 0.112, and I get the friction force, 3.517. Now, you want to round that to 3.52, but I saved this for calculation. So the net force then, I didn't write this out, is going to be, just do that, it's going to be F parallel minus F fric and that's equal to MA. So this is F parallel minus F fric is the net force. So I took the 9.24 and subtracted the 3.517, and I got 5.72 newtons for the net force. And then in order to get the acceleration, I just divide the net force by the mass. And I get the acceleration of 1.71 meters per second squared. Good. We're done.